I'm Adesh Abang and I'm from Mumbai, India, and I work at Intuitive.ai as a data and AI ML engineer. And over there, like I work on data pipelines, I work on ML pipelines, and today we'll see a part of that, like how do we process video data using Apache Beam? How do we scale those? Like how do we scale all this stuff on large scale? So let's start. Talking about video data, it is highly unorganized, unstructured. So pre-processing it before creating quality data set is a must thing, which help us like in processing our ML models later on. So let's begin. So what are the challenges while processing videos data? Like how do we scale processing video data? First problem, the storage and input output bottleneck. So like traditional data or ML pipelines, they work on the concept of like download first and then process. We'll see how Apache Beam helps us in processing like hundreds and thousands of videos, uh, like in at fly. Next, temporal data complexity. So video is a collection of individual frames, but a frame may be an image, but in videos, multiple actions are happening. And to capture those multiple actions, we need to capture the temporal complexity of the video. And for that, we are using sliding windows. We'll see going ahead in the session how are we using sliding windows to capture the temporal complexity of the data. Next is the black box inference trap. So like videos are like raw clips. To convert those videos into high dimensional feature vectors like quality data, we need to use like models or run inference to get into right shape before using it for training. Let's go ahead. So the pipeline which we'll see today, there will be 6 stages for of those pipeline that will be using GPU, and it will be scalable, parallelized at each and every stage. So the first stage, which is video segmentation. So at this stage, we'll have the raw video. We'll use the beam transform called Splittable DoFn function. It will split the videos into multiple segments, and multiple workers will work on extracting frames from those clips or those segments in stage two. At stage two, the frame extraction will happen, wherein we could like a video may have like lakhs of frames, maybe 80,000 frames, maybe 2 lakh frames. Like it is a huge amount of frames to be handled. And there are many redundant frames. Like if you are extracting frames at like each and every frame at like the FPS at which the video is, it will be a huge amount of data at the end of like data processing. So what you could do at this stage is like you could extract the frames at a particular FPS. So for example, the video which we are using today is a 60 FPS video, but we are extracting frames at 10 FPS. So what we are doing is we are extracting every sixth frame of the video. So we don't have a lot redundant data going ahead. We also need to resize the frame as per the model which you are using, right? Next, moving ahead, stage three, sliding windows. We'll look how we are using sliding windows to create clips, how we are using sliding windows to add the temporal complexity into our pipeline, into our data processing stage. Next stage is stage four, beam run inference. We'll see at this stage how we are using the beams run inference transform and the model handler transform to like create raw videos into highly meaningful feature vectors, which will help us in training models. Next step is stage five, label alignment. So there could be a possibility like with video data, you could also have CSV data, you could also have JSON data or a normal text file. Taking example of like a patient data at an hospital, there may be age, like what disease he is suffering, along with video. This type of data will also help us like creating meaningful ML models, like meaningful predictions. And at last stage, the output which we'll write as sequence examples, which will show us continuity, like as per the video output. So going ahead, Now, let's see the stage one. How we'll use splittable do function. How splittable do function works in like parallelizing or splitting the task among the workers available. So in this example, for example, we have 10 workers. So we need to like divide the task into 10 different workers. So phase one of the splittable do function, what will happen over here is like we have the video and there is a concept called restriction tracker in splittable do function transform. What it will do is calculate the amount of frames in that particular video. So for example, we have 60,000 frames in a particular video. So it will create a restriction tracker and it will track those 60,000 frames throughout the processing or throughout the frame extraction. Going ahead, once we have the restriction tracker, we go to the phase two. So we could either use static splitting or we could use dynamic splitting. The beam splittable do function transform provides both the options. In static splitting over here, we could specify like to divide the video into chunks of 6,000 frames. So for example, 60,000 frames, each chunk of 6,000 frames will have 10 chunks, dividing them into 10 workers, which will like speed up our task 6 times. And over here we get the restriction provider. So like we get the video, we split the task, phase two is completed, and we provide it to the frame extraction tool, whichever we are using. For example, you can use OpenCV and other third-party tools available. So the phase three is the phase where magic happens. So for example, you have 10 workers working on 10 different chunks of work, but one worker has completed its task and there is another worker which is struggling to complete his task and it is stuck at a point. So over there, this try claim per frame feature comes into the picture. What it does is like a worker which has slowed down, it like again divides the frames which it has got into the new worker or the worker which is free, which like which doesn't halt the pipeline and keeps the work going on smoothly. So this was the part of splittable do function. Next, we'll see the frame extraction engine. So you could either use OpenCV for frame extraction, which is like NumPy based sequential reading, or you could use OpenCV, which allows random access for like a more faster and scalable workflow. So once we have the frame extracted from the video, the next thing we'll do is assign timestamp or assign event time to every frame in our video. Why are we so you'll ask like why are we attaching timestamp to each and every frame? So at the next stage, when we'll use sliding windows, like when we'll bring in the temporal complexity into the picture, assigning timestamp to each and every frame is like a very important thing. So we attach timestamp to each and every frame at this stage. So we have timestamped value, which is frame. Frame will be frame ID, and the timestamp which we are attaching calculated using this formula, like timestamp equals frame index divided by the FPS of the video. So, but the thing is why timestamps matter, as we spoke, like, so to use sliding windows, we need to attach timestamp to each and every window frame, because sliding windows work on time-based events only. All right, going next. So let's like now look at the sliding window part. So for example, you have 40,000 or 50,000 frames extracted from a video and you have created and like to process video data to capture temporal complexity of that data, you need to convert those frames to clips. So why we need to convert those frames to clips? Because there are several actions going on in a particular video. Maybe if you look at take example of like a football match, there may be a player kicking a football into the goal, but there may be a keeper diving too, there may be a defender making a tackle. There are many actions going on, and to capture each and every millisecond or second of action, we need to use sliding windows. We'll see with this example like how we are going to use sliding windows to bring in the temporal complexity while video data processing. So as you look on the screen, there are like 0.1 seconds, 0.1 second segments being created. So each frame it's attached with 0.1 second timestamp. So 0 is the first frame, 0.1 second is the second frame, 0.2 second is the second frame, 0.3 is the third frame, 0.4 is the fourth frame, and so on. So what we'll do is, so for example, you see on the screen, so window 1 is from 0.0 second to 1.6 second. So it will have 16 frames in a particular window. So 16 frame, so the size of each and every window that we are using in this example is 16 frames. And if you look at the window 2 example and the window 3 example, it is going ahead by 0.1 second, and then it is going ahead to 0.2 second. So the stride which we are using is 0.1 second. So what we are doing here is like we are not even like letting go a millisecond of data, which could like create any difference in making predictions going ahead. And Beam provide, so Apache Beam provides two types of windows. One is fixed windows and another is sliding windows also. But why are we using sliding windows? Why not fixed windows? So like if you use fixed windows, it would be like 0 second to 1.6 second, then 1.7 second to 3 seconds. So what will happen over here? So between 1.6 second to 1.7 second, in between those milliseconds, there could be an important action going on. You could miss that particular action. But using sliding windows, you can see your every frame appears in 16 different clips. So each and every frame appearing in 16 different clips makes it like uh, high and quality data, which will like create next. So you can see on the screen, each window we get 16 frames, and those 16 frames we create into one video clip tensor for X3D model. So talking about X3D model, it is a feature extraction model that we use to extract like high dimensional feature vectors from ML models. There are video transformers also that you could use. There are swing transformers that you could use for extracting features from the video. So if you look at the code snippet below, so sliding window size we have provided is 1.6 seconds. So it will have 16 frames per window, and the period, which is the stride, it is 0.1 second. So it will go ahead while 0.1 second for per window. Going ahead. So once we have those clips created using sliding windows, we also have the temporal factor, temporal complexity attached to our frames, to our clips. So we have our clips ready. We convert those clips to tensors. So why do we convert those clips to tensors? So all the machine learning models do not handle like they do not take an input like raw clips, raw videos, raw images. They need the input to be as in the format of a tensor. So we convert the clip, the 16 frame clip which we got in the previous stage, into a particular tensor. And this tensor, if you see, so B, C, T, H, W, what does this mean? So B is a batch, C are the number of channels, T is time. So we added temporal complexity over here. So if it was a 2D tensor, we would not have the temporal complexity, then the height, then the width. So once we have the clip tensor, so Apache Beam, so next going towards the keyed model handler, which will help us. So Apache Beam provides two different model handlers. One is keyed model handler, other is like an unkeyed model handler. So why are we using the keyed model handler? So for example, if you are going to process 20 or 30 or 100 videos at scale, so the frames and the clips of those videos, like while it is processing parallelly, could get like mixed with each other. So the keyed model handler helps us in this case because each clip or each frame will flow in the pipeline with a key, with a video ID, with a frame ID, with a clip ID, which will help itself to identify like I'm belonging to this video, I'm belonging to this clip, for example. So for this example of ours, and for most of the examples, keyed model handler is being used while processing video data to like track videos, track clips throughout the pipeline. So in the bracket below, you could see PyTorch model handler tensor. So Beam provides different frameworks model handler tensors. So for example, PyTorch, TensorFlow, or else there is also an option you could use custom model handler tensor, wherein if you are using a model of your choice, at that time you could use those model handler tensor. And in this case, in our example, we are using this X3DM model, which is a PyTorch model. So we are using the PyTorch model handler tensor. And so at the last stage, as we saw, we created the clips, we converted them to tensor, we gave it to the keyed model handler. We have the video ID, we have the clip ID, we have the frame ID. Now next step is giving it to the model for run inference. So beam Apache Beam also provides a run inference transform, which like helps tracking the keyed model handler, the keys throughout the model. Like, so over here training will happen, not the training of the model, but we are extracting features from the unstructured or unorganized video data. Well, the output of this XGDM model will be high dimensional feature vectors, which we'll use later for model training, predictions, anomaly detection, or many other examples. So let's look at the code snippet, which is on the screen. So model handler, the keyed model handler, which we saw, it will track the video ID, clip ID, frame ID. Then the PyTorch model handler tensor, as we are using a PyTorch model. Then the stake dig path, what it does, it saves our model weight. So whatever model you guys are using, you need to store the weights of those model in the state dig path, or from where the run inference model or the run inference transform will load the weights and then process all the clips, all the tensors, and give us like the feature embeddings we need to use. So the last stage, we get all the feature vectors, embeddings. So why run inference? So why we use Apache Beam run inference transform? It does auto batching. We don't need to like do custom batching ourselves. Then keyed model handler, as I said, it like tracks the video ID, clip ID throughout the inference. Then we are using GPU, so we need to use the CUDA drivers throughout the inference. Then so at this stage, what until this stage, what has happened? We got video, we got frames extracted from the video, we got created the clips using the frames, then we converted the clip to tensor, then using those clip tensor, we got meaningful feature vectors or meaningful feature embeddings. The next step. So as we spoke in the beginning of the session, there could be a chance you could also have like a CSV data, JSON data, or any text data. As we took the example of the healthcare data, there might be patient data stored in a CSV file. So how our pipeline will work, there will be one branch of processing video data, which we saw, and the other branch will be the label data. So processing video data will be also similar to the video data. The only thing is we don't have to process videos, frames, and clips over this, but we will be also attaching timestamp to the label data which we got to like create synonymous synchronization between these both video files as well as the label files. So as you see in the screen, so run inference produces two separate peak collections. One will be video ID, then the window start ID. So the CoGroupByKey feature provided by Apache Beam helps us to join features with like from two different P collections. So the two different P collections which we have got is, if you see in the diagram, the feature P collection and the label P collection. The feature P collection, so for example, the key is the video ID, and then the clip ID which we'll use, which will be the first frame of a particular window, which is what we'll use to join two different P collections and create our final data set. So what is happening at this stage is we are basically joining two P collections or two branches in which we have processed the data. One is the video branch, other is the label branch, and we are basically joining these two data P collections to create a unified final data set, and writing is as quality TF sequence examples, which we'll use further for like training ML models, predictions, anomalies, etc., etc. So let's look at some of the pipeline results which we have got. So if you see the first diagram, there are around 7 labels over here. So we have 7 labels in this data set. It is public data set available. It is a surgery data set, SARR 50 data set, which we are using over here. So it has around 7 labels. Over here, you could see how the temporal complexity is being maintained. So from 0th frame to 2000 to 4000, 6000, 8000 to the 14,000 frame, how each and every label and feature vector is like divided. You could see the class proportion over here, all the 7 labels. So taking example of a single video which we have processed. So we have 2564 clips in this video. The frames are around 15,000. Action classes which we have over 6 to 8. The sampling rate which we are using, so as we discussed in the beginning, we are extracting every 6th frame. Then the feature vector which we have got, it is like 408 dimensional feature vector, and then we are writing the final sequence example. So this is the example of like output of a particular video data which we are getting in the end. And let's now look at some metrics, the pipeline metrics, how well it is performing. So firstly, let's look over here. So we are sampling video at every 6th frame, which is at 10 fps. Then we are getting 16 frames for a particular clip. Then our window duration, as we saw, the sliding window duration is 1.6 seconds. Then the feature dimension, which we are using 2048. Then we'll see like how a normal pipeline, how a pipeline with 2 workers and how a pipeline with 10 workers will like increase our speed. And then we are using GPU as mentioned. So a normal sequential script for 10 videos processing of data will take around 70 minutes, 60 minutes, 80 minutes, depending on the size of the video. If the average size of a particular video is around 15 minutes, it takes around 90 to 100 minutes, a sequential video data processing pipeline. With Beam, we are making it like faster, even like double. So for processing video data with 2 workers using Apache Beam, it takes around 20 to 25 minutes, depending on the video size also in this case. And if you are using 10 workers, so processing 10 videos with 10 workers takes like processing only 10 minutes. So you are processing each and every video within a minute or like for a minute, and you are creating quality data set within 10 minutes for 10 different videos at a highly scalable pipeline. I think we are done for the session.